title of this talk, which might be different in writing, is actually Major Merger History of Massive Galaxies since the Z equals 3.
Thank you. Can everyone hear me okay? Yeah. Awesome. So, like this, introduced, so I am Kameswara Mantha. I'm a graduate student at University of Missouri, Kansas City. I work in collaboration with the UMKC Galaxy Evolution Group, from which you'll hear a lot of good talks tomorrow. So today I'm going to talk about the primary crux of my PhD thesis, which is dealing with major mergers of massive galaxies since redshift of 3, which I indicate by Z of 3. So before I jump in, I wanted to emphasize my primary research interest, which is to understand the role of galaxy mergers. Galaxy mergers are when two galaxies gravitationally interact with each other over a course of time to coalesce to form one more massive system. This process is called as galaxy merging. And I want to understand the role of galaxy mergers in transforming galaxies as in their physical properties, such as their shapes and how much mass do they have, the stellar mass of galaxies. And here's a schematic diagram of two galaxies sort of interacting with each other over time and then coalescing into one single object and in the end turning into another more massive galaxy. And many studies over the past few decades have emphasized major merging of galaxies, merging between similar mass galaxies as a primary mechanism for forming galaxies that are elliptical, round looking and more massive. I want to understand to what extent does collisions between galaxies transform galaxies. That's my primary research interest. So to understand how do we quantify the importance of galaxy merging, there are two important steps. One is to first identify which galaxies are colliding with each other and which are not. The other thing is to quantify the rate at which galaxies are colliding with each other as a function of time in the universe. Are they colliding, do we find more and more galaxies to be colliding in the early universe or not? That's the primary question that we are trying to ask. So, first, in order for us to identify galaxy mergers, there are two primary ways you can do it. One, observationally speaking. All we do is take a telescope and point it at the sky. How do we know if the galaxies are colliding with each other or not? There are two ways of doing this. One is called as the close pair method, where you identify galaxies in close physical proximity to each other and select them as plausible mergers, meaning that they will merge soon. Here's an example image from the Hubble Space Telescope of two galaxies, each of 100 billion solar masses, colliding with each other that are 7 billion light years away from us, meaning that you're looking at them 7 billion light years ago. And one way is to select them as a close pair, they're right next to each other, and they're also colliding with each other in terms of their velocities. They're bound to each other gravitationally. The other thing is to use these really hallmark features where colliding galaxies create these features called as tidal features due to tidal forces, and using them to identify merging is another technique. In this talk, I'm going to focus on the close pair method. Okay? So, just to reiterate, close pairs are selected based on their proximity, and you can use different quantities such as the projected distance between them, the mass of the galaxy 1, mass of the galaxy 2, and what is their 3D separation. Okay, that's what that delta Z is. So one of the simplest equations that I'm going to show is to quantify the merger rate, you need two quantities. One is the close pair fraction, fraction of galaxies in your sample that are in close pairs. That's literally the first numerator here. The denominator is something called as the observability timescale, and this is key. And I want to show a simple video before I jump in, because this is a key quantity that will dictate on how accurately we can compute the merger rate of galaxies. Because if you want this, you need this and this accurately. So observability timescale is the timescale during which you can catch a real merger in the universe in its close pair state. So in this movie that I'm going to show, you see that two galaxies are merging, and I'm trying to, so the timescale is the fraction of time that it shows up as a close pair. And in this axis, I'm showing the projected distance with which the galaxies are moving towards each other, and when it reaches 0, that means that it's collided. Okay? So this time, if you add up the time on this axis here, you're going to get the observability time. But this can only be done using simulations, because you cannot really go out in the universe and see galaxies colliding with each other in real time, because we'll die in like 100 years. So you cannot really see them collide with each other. So we cannot only do these with simulations. So what I'm going to do is to quantify this time scale. And how do I do that? So first of all, in simulations, we can identify the merger rate of galaxies, the true merger rate of galaxies, because we know in the simulation how many galaxies are present, how many of them are colliding. So Vicente Rodriguez Gomez et al. 2015, they have measured the true merger rate of galaxies in the simulations, and the key punchline that they found is that in the early times in the universe, there are a lot more galaxies that are colliding with each other. In the nearby universe, in the present day universe, there are not many colliding with each other. But in the same simulation, another study went in and measured the fraction of galaxies that are in closed space. And they found that it was flat. I want you to take a note of the trends here. This is flat and this is increasing. And this is a problem. Because if you were to assume that the observability time, which is the denominator, is a constant number, which many studies in the previous literature have used. They have simply assumed that it's a simple number that does not evolve with any parameter. If you were to simply divide the fraction that looks flat, which is on the y-axis, with a simple number, it's going to start to disagree with the actual merger rate of galaxies. And that suggests that the time scale needs to evolve as a function of redshift. That's the primary indication. I want to understand how does the time scale evolve with redshift. That's what I want to know. So here's a schematic diagram of how I'm going to do it. So on the y-axis is the merger rate. If I know the true merger rate inside a simulation, and if I can measure how many galaxies are in closed space, and I can simply divide the pair fraction with the rate, and I would get a time. That's what I'm going to do. So in order to do that, I'm going to use something called as semi-analytic models. So in order for me to generate mock universes, I'm going to use something called as semi-analytic modeling of galaxy formation, where I take the output of the embodied simulations, dark matter only simulations, and they literally just analytically, you write down formulas on how galaxies evolve, and n comes a mock universe that you are looking at all of a sudden. And what I'm going to do is I'm going to take this mock universe and observe galaxies in closed space. And I know the true merger rate in that simulation, and hence I can compute the time. That's my hope. So what did I do? I took one of the most recent and a novel semi-analytic model called as the universe machine by Peter Beruzzi in 2018. And what I did is I computed the pair fraction on the y-axis as a function of redshift. And I want you to observe that the pair fraction is flat, again, confirming my previous other studies as well, which is shown in the open points. That's flat, and I'm also finding a flat pair fraction trend. But the true merger rate here is increasing. So what I do? I said, okay, I'm going to divide that and find out how the time scale needs to evolve. When I did that, I found that the time scale needs to evolve in such fashion with a power law slope of negative 1.6. What does this mean? Having a power law slope of negative 1.6, what does this physically imply? This means that at higher redshifts, i.e. back in time when the universe was a baby, the galaxies that were colliding with each other were being observed for a short period of time, meaning that they're colliding faster essentially. That's what's happening. So this is actually slightly in disagreement with another study done. And for the first time, I'm able to do this in a Bayesian way and also give an error bar on the time scale. So this is something that I'm currently doing, and in the future, what I'm going to do is I'm going to complement this study by using the hydrodynamic simulations and literally following galaxy mergers in this fashion in their closed space state and measure the time scales. And I have a suite of 6,500 galaxies mergers and almost 1 million images to do this exercise. So that's what I'm going to do. So I just want to leave with my three key takeaway points. I just want to emphasize that the time scales are really important and we need to understand them better. And I'm going to use the semi-analytic models to compute that, and I'm also going to use the simulations to measure the time scales. Those are the three key takeaways that I want you to take away from my talk. Thank you.
Are there any questions?
So is the time scale you're talking just how long it physically takes from the start of a merger to a single galaxy?
No. So that's slightly different from what you just said. So just to reiterate that question, he asked that if the time scale that I'm talking about is the same thing as two galaxies, the time taken by two galaxies to merge, that's different. So the observability time is, let's just say that if two galaxies take 1 billion years to merge, okay, I'm trying to observe them with a given specific condition, like looking them through a window. If you have a small hole and if you are trying to visualize them as if they are merging, you'll only see them not for a gig a year, but you'll only see them like half that time. So that time during which you're seeing them through a window is the observability time. And that's the important quantity, not the time which they take to collide with each other.
What kind of equations is your model solving?
So these simulations were run with hydrodynamics, where you take dark matter and then you simulate dark matter and then simultaneously you put in baryonic physics into it. I'm not an expert on that simulations. These simulations were run by a separate group in Durham, if I'm not wrong, in UK, and they include a lot of other like baryonic physics means like supernovae, feedback, and all the messy star making processes that are involved. I'm not an expert on that, but I have the data set from them. So these are some leading simulations in the current market.
Stupid question. Do galaxies contain black holes?
Yes, massive galaxies at least, from current literature, from what we know, and I'm sure we'll hear more talks tomorrow about the black holes in galaxies. But yes, massive galaxies do host supermassive black holes. And actually there was a recent first image of the black hole that we saw a few weeks ago is in a huge elliptical looking galaxy that's eating stuff, and that's why you see that accretion disk, and that the image that we saw is of a supermassive black hole, which is 6.6 billion solar masses times the mass of the sun, so it's huge.
Okay, any other questions?
Physically, is there a reason you can think why the merger rate, so the observability rate and the merger timescale are related, right? Just how fast it's going in and out of your window. But why would it be faster in the past? Like conceptually, why would galaxies want to merge together more quickly?
So, from what I understand, the mean density of the mean density of the universe at that time, in terms of when I'm talking about mean density, I'm talking about the dark matter, because galaxies live in dark matter halos, and the primary thing that's driving the merging of galaxies is the merging between the dark matter halos itself. And then on an average, the universe is smaller back in time, and it's denser, so that relatively speaking, they're closer to each other, and they're interacting gravitationally. They're merging with each other. So that's something that conceptually speaking, that's what I do.
Okay, let's thank Kameswara again.